I wanted to thank the Natural History Institute for having me and for making all of this possible. They have worked all afternoon to get the technology ready so that you could see it clearly and hear it clearly and have seats, etc. So thank you all. I want to thank I wanted to ask, how many of you started your interest or perpetuated your interest in geology by coming to the Central Arizona Geology Club meetings? How about hands? Wow, okay. And that was made possible by Debbie and Harry Allen right here. They started it and ran it for 15 years, 12 years, and it was pretty amazing. We had big turnouts. I also wanted to ask, just because I'm curious, how many of you took a class from me? Wow. Thank you so much. Wow. Okay. Well, you're going to see me seated, which isn't my norm, but I had a knee replacement this winter, and by later in the day, like now, my knee gets cranky. And if my knee is cranky, then guess what? I am too. So I'm going to sit down. We're going to, as she said, save questions till later. But if you see something that doesn't look right on the screen, ignore it. No. I hope it all goes okay, and let's get going. Okay. Most of the photos here were taken by Harry Allen, as in the book as well, but that wasn't the case when I put this together, this front page together a while ago. And one of the things that people often try to associate is Granite Mountain with Thumb Butte, because they're both igneous. Well, that's about all there is to the association. They're a billion years, more than a billion years different in age, and they just happen to be proximal in location. So they're not related, okay? But just thought we'd throw that in. Okay, let's see if I can make this work. So the contents here, I'm going to go over just a little bit of background about why I started this research on Thumb Butte, and then I'm going to tell you what we know about Thumb Butte. I published an article more than 20 years ago, so basically that's what we know is from what I published in that article. What we don't know about Thumb Butte, and basically what it looked like, which is what everybody wants to know, what was it, and how much erosion has taken place, how much modification has happened to its appearance. And then at the end there is theories about its formation, and I'm not a volcanologist, and what I've come up with, the conclusion is simply the elimination of all the other possibilities, okay? So it's not that I'm some expert volcanologist, it's that all these other things don't make so much sense. So that's the way it's gonna go. Here we go. My background, you already heard it, almost 40 years, more than 600 days of field trips, and during that time, maybe even some of you specifically would ask, well, what is Thumb Butte? And I didn't have the answer. And for my first 10 years or so here, I kept looking around, looking over my shoulder, expecting someone else to answer that question. And for those of you who know, Medora Krieger mapped this area back in the 50s and published in the 60s. She was a USGS, the first USGS field geologist who was a woman. But she didn't really do much with Thumb Butte because she was given tens, 20s, hundreds of square miles to cover. So Thumb Butte is a tiny feature when you look at it in that respect. So that's what got me going. I started with Thumb Butte, and I called it grandly the Tertiary Volcanics Project. And I have boxes and boxes in our shed called Tertiary Volcanics Project, and they just have rocks in them. I collected samples from Thumb Butte with the permission of the Forest Service and lots of other volcanic rock samples around town. I did it over a period of about 4 years. The USGS via Ed DeWitt, who was in the Denver USGS office, but he did his doctorate work here in Yavapai County, so he had a soft spot for our geology. He's the one who got my samples analyzed. And whole rock geochem and all of that can be very expensive, and he made sure it was covered. I spent a year at the University of Canterbury in Christchurch, New Zealand, about 25 years ago, and at the time I was just trying to work the raw bits and pieces into a real study, and they helped me a lot. They were very supportive. And the following publication, which is what you'll see on the next page, was the result of that. Thumb Butte, a latite among tertiary basalts. It was published in 2001. You don't want to read that. You see the problem there? Yeah. It's a very heavy, I wanted you to see. Let's see. It's called the Mackin volume. It was a peer-reviewed journal article, but nobody has read it because why would you, right? Right? So tonight I will try to summarize what that was about. Just a note, because I called it the tertiary volcanics, I will see my screen better if I don't have these glasses on. There are lots of tertiary volcanic rocks around town. Thumb Butte is by no means the only one, and it's actually a little atypical. It's not the typical basalts. And I put the arrows on that map. The red arrow is Thumb Butte, and the variations of blue are all those other more typical volcanic rocks. There's Glassford Hill. That's Glassford Hill right there, that big gray blob. There's things out here. That's the north side of town, just south of Willow Lake Road, all those pink ones. And then there's a great big chunk out Williamson Valley Road. So we have a lot. And I did sample all of them. So here's remember I said there was going to be a little introduction. We've done that. Now here's what we know. So the first thing, what we know is its appearance. It looks dark gray on the outside on weathered surfaces, but if you get a fresh surface, it's light gray. It's uniformly fine-grained, that is, the butte itself doesn't have any difference in grain size or crystal size from top to bottom. It's uniform, it's homogeneous. And it's got these conspicuous phenocrysts, which are bigger chunks, visible chunks of the black mica called biotite. And typical basalts, the dark mafic lavas, don't have biotite. So that's a key right there. In addition, there's no brecciation. So I put a breccia there, that one on the bottom. That one's a breccia because it's got chunks of other rock in it, angular chunks. That's common in things, volcanic necks or diatremes like shiprock, and there is, as you'll hear, almost none of that. I said almost. Okay. What we know about Thumb Butte number 2, its composition. It's not a basalt, which is what all those other, Glassford Hill and all those other volcanic, the lava flows around town are basalts, and it is not. It is, depending on which systematics you'd like to use, it's either called a latite or a trachyandesite. They mean the same thing. I think what I chose here calls it an andesite. A trachyandesite. And the values that make it different from a basalt are the silica, the sodium, and the potassium. And the silica is a little higher, and so is the sodium and the potassium than a typical basalt. Well, I think it's pretty easily explained because all the lavas in town had to work their way up through a granitic country rock, the granite that was all around here because that granite's older. And if it picked up a little of the granite on the walls as it worked its way to the surface, it could pick up silicon and potassium and sodium. And you might say, well, then why aren't all of them that enriched? Well, the other ones are younger, and they came up through fissures that had already been coated. Thumb Butte is the oldest of the tertiary volcanics here in town, so it would have been the first one. I hope it's true. I'm telling you it is, but I don't know. What we know about Thumb Butte is its age. It's 14.79 plus or minus 0.15 million years. For a comparison, Shiprock's almost twice as old. This rock was determined using argon-argon age systematics. It was done by the New Mexico Geochron Research Laboratory in Socorro. Bill McIntosh was the boss there at the time. He did it gratis for me. And you can't read that because it's too small. But I went to a course offered by a man named Charles Ferguson, a volcanic rock mapping class. And I was in it, and Bill McIntosh was in it. So Charles introduced us. And I was talking to this man when I found out he ran a dating lab, and I said, ooh, I have this rock that I'd like to have dated. And we were down in the superstitions. This is 25 years ago. And he said, well, you don't happen to have it with you? And I said, actually, I do. I carried that rock around in the back of my Honda Accord forever. So I handed it around. We were standing in the parking lot, right? We were actually standing behind my car. I just had to pop the rear and hand him the rock. So this is the oldest. Oops, didn't mean to do that. Too many buttons. It's the oldest of the local basalts, as I said, and so that is why I think it came up through uncoated fissures and picked up a little bit of the composition of the surrounding rocks, okay? It is named the Hickey, it's part of the Hickey Formation volcanics. Hickey Mountain is just as you pass the power line as you head to Jerome and on the left-hand side of the road. Typically, lava flows are not given names, unlike sedimentary rock formations, but this one has some things that look kind of sedimentary in the middle of it, so 60, 70 years ago, they gave it a formation name. Those of you who took a class from me probably realized I never used that name. I think it's odd, but that's okay. So what we know about Thumb Butte number 4. I took on the butte 15 oriented samples. So when I took the sample, I measured what was compass north and what was vertical. And then I took those samples, I actually took them with me to New Zealand, and they made what are called oriented thin sections. So we could tell in 3 dimensions what it looked like. And they, again, that was gratis. They did that for me. I taught there for a year, and they were kind enough to do that, 15 thin sections. And this is the one that really was the most convincing. You can see in there, why does it, that's not the one that says it's supposed to go forward. That's the one that's supposed to do the little circle of light. Anyway, you can see the blue arrow shows you the flow direction. It's pretty obvious. The flow direction is from the top to the bottom. And then once it gets from the back to the front, if you will, if you're standing down in the park, what is the back side to the front side? That's the flow direction. And then once you get down to the front, all the little flow indicators, instead of being, they turn perpendicular to the flow right at the edge of it. They kind of like branches in a stream. They turn sideways to the flow right at the end of the flow. So that was very persuasive for me. Volcanic necks don't show homogeneous flow directions from one direction to the other. That's when lava comes up from a central vent and you're right there. Lava flows show flow direction where it comes up here and then flows downhill. So the minute I saw this, I started reconsidering, wow, this is very persuasive that Thumb Butte is the remnant of a lava flow, and all of the 15 thin sections were in agreement. This is the most persuasive one, but they were all indicated the same flow direction, okay? And that, to me, was very persuasive that this is a lava flow and not a volcanic neck. Okay. Oh, did I show you how big the field of view is? 3 by 2.5, 2.2 centimeters. So a little bigger than an inch by an inch. Then again, the USGS did these geochemistry analyses that helped a lot. And rubidium and strontium and barium and strontium are typically used to differentiate igneous rocks one from another. And they're pretty sensitive, so you can see a lot by them. So this one is a rubidium strontium. Rubidium is on the vertical axis, strontium is on the horizontal axis. And this is showing over here in the box. This is going to go forward, I'm afraid. Yeah, I don't get it. It's not doing where it's supposed to be, but the circle. Anyway, when I did that, if you go to the box, Thumb Butte is those little triangles. That's not a triangle. A square on a side. What do you call that? Rectangle, yeah. Anyway, where the arrows are is Thumb Butte. Thumb Butte over there in the explanation, and then Thumb Butte on the graph. And you can see that local rocks, the Sullivan Buttes, Water Tower Hill, which I've hardly mentioned, and the other Hickey Formation rocks are all distinct. You see, they really do separate out. So this was very persuasive. And remember, I just sent these off. I didn't know what it was going to look like when it came back. So I was pleasantly surprised to see this. And we'll come back to Water Tower Hill in a minute. It's very, very close to Thumb Butte. And a few of you have probably gone up on Water Tower Hill with me. Is that right? Yeah, Bob, you guys have? Yeah, you did? Okay. It's very close to Thumb Butte, but it's not exactly. Okay, so we'll go to the next one. Oh, by the way, you want to know what Sullivan Buttes is, because I've mentioned it. Sullivan Buttes are volcanic lumps and bumps just north of Chino Valley. And I love this picture, Harry Ellen. I love this picture. I think it's actually in the book, but that's a very nice picture of the Sullivan Buttes. They're twice as old, so they've lost a lot of their singular character. They've experienced twice as much erosion. Okay, so they're just not as sharp as some other features you might expect. Then also more on these on this geochemistry. This is barium versus strontium. And again, barium on the vertical axis, strontium on the horizontal. You don't need to know all about these elements. It's just that they're sensitive indicators of the provenance or the source for igneous rocks, okay? And so again, I put an arrow on the Thumb Butte samples, and look at that. They really group differently. Now, they're pretty close to Water Tower Hill, and they actually are very close geographically as well. But you see these other things, the Sullivan Buttes and the other Hickey Formation, they're quite a ways from those geochemically. Again, these were results that I didn't know. You know, he sent off rocks, collected samples, sent them and had them analyzed, and then got back this reams of data, and this is what fell out. It was very gratifying, if you will. Okay. Oh, gee. I think this one, yeah, got ahead of itself. I had trouble right this afternoon with 2 slides that wouldn't, I thought I had jumped them. This is what we know about Thumb Butte 6. It has cooling cracks, and you've all noticed them. They are crude and not as nice as cooling cracks in Iceland or Scotland, or what's the one on the east side of the Sierras? It's called Devil's Postpile. Those are so regular and so beautiful, but these are still columnar joints, cooling cracks, okay? So let's go back a moment, because I got this one out of order. So comparisons, so I think that's Devil's Postpile there. I put in a little bit about columnar jointing if you're not familiar with it. It forms in lava flows, hills, dikes, ash flow tuffs, which I just drove past some ash flow tuffs that were columnar jointed just south of Caliente, Nevada last week. Really striking, huge joints. They tend to have 5 or 6 sides. They can have 7. Here they are. By the way, there are some other columnar jointing in town over by Debbie and Harry's house in Hazley. Hazley Homestead has some up on the Water Tower Hill there. But what is important, and I put it in bold, is the growth is perpendicular to the surface of the flow. So if you have a flow that's on a horizontal surface, the columns will be vertical. If you have a flow that's on a sloping surface, the columns will be perpendicular to that slope. And if you have a dike that's horizontal, some other orientation, the columnar joints will be that other orientation, okay? So they're a good indicator. So let's go and see a couple examples here. Sorry, same one. So this is a horizontal jointing in a dike in Colorado, and this, by the way, Ms. Joanne, is the photo I had to get permission from. You said it was it John? John Hopkins, for those of you who knew Cleve and Lillian. I ended up talking to their son to get permission, and I didn't even know it. And I finally said, wait, this wasn't your parents, and it was. So this is a expanded picture on the right. So this is to show you that the cold sides were either side, and so the columnar joints are perpendicular to it. That's how they develop. But this is in a dike. So Thumb Butte isn't a dike. Okay, Thumb Butte isn't a dike, but let's keep going. More horizontal jointing, horizontal columnar jointing, this time in Church Rock on the Navajo Reservation. And some of you I walked around Church Rock with. For those of you who remember us walking around the backside? And what's very cool, this picture isn't really great, and I didn't take one when I did it, but the horizontal jointing there is, the jointing is horizontal. It's parallel to that arrow, and I don't know if you can see my little red lines, but those are to outline a columnar joint that's horizontal. If you ever get a chance to go there, they're spectacular. And that's what's left of a dike that was intruded through the pre-existing sediments about 25 million years ago. Okay. So here's our recap. We know what its composition is. It's not a typical basalt. It's a basalt with excess silica, excess sodium, and excess potassium. Its appearance, it's uniform. That's important. From top to bottom, side to side. You go crawl all over that thing, and it's all the same texture. And there's no breccia on the butte itself, which kind of eliminates a volcanic neck or a volcano itself right there. They're always brecciated. Its age, almost 15 million, which makes it the oldest of the local tertiary volcanics, the Hickey volcanics. Mineral orientation, it suggests flow from the high side. Geochem, there were some similarities to local Hickey basalts, and you might say, but they were way far apart. Well, if I gave you a big graph, all of those would have been in the same area, and other igneous rocks would be all over here. But I chose to expand a graph, so it looks, I wanted you to see that they're not the same, but they're not really different either. Can't have it both ways, huh? Then the vertical columnar jointing is like that found in flows, unlike that found in dikes. So, then here's what we don't know, the last bit. How much erosion has taken place and how that has modified its appearance. And the second was what form it took when it erupted. Was it a lava flow? Was it a dike? Was it a volcano? Specifically, was it a volcanic neck or a dome? All these were possibilities, okay? And I think when I wrote that paper in 2001, I was leaning toward a dome. I can't even remember, but I may have said that. I've since learned a lot more about domes since then, and we'll get to it, but I don't think that's so. Okay. Okay, to consider rates of erosion. It's hard to estimate. We haven't been around for that long. But Red Butte in northern Arizona, on your way to the canyon, the lava at the top of Red Butte, the basalt, is 8 million years old. And so if you can reconstruct the whole plateau, was that red arrow is 600 vertical feet. 600 vertical feet has been eroded away from the plateau in the last 8 million years. That was a horizontal surface when that basalt came out. So if you do the math, 600 vertical feet over 8 million years, you get roughly an inch per 1,000 years. This is a gross simplification, and it's going to get grosser here in a minute, and note, the Moenkopi is relatively soft as rocks go. How many of you have climbed up Red Butte with me? Yeah, we did that multiple times. Okay. This one is the most complicated slide of the show, and I tried to simplify and I couldn't. Okay, to consider rates of erosion, and this, by the way, thank you, Walt, for such a lovely picture. This is one of Walt Anderson's. If you don't know, that is Glassford Hill in the background. It really is a volcano, and it really is basalt that came out of it, and it's a little younger than Thumb Butte. It's about 13.2 million years, so it's a little younger, and it's truly basalt. There are places where that basalt lies directly on the Dells granite. Meaning, so when it was erupted, 13.2 million years, the Dells granite was exposed at the surface, and you can measure what the elevation was at the time, okay? So I took the difference, and that red arrow is about the highest point on the Dells granite where the basalt from Glassford Hill is directly in contact with it. Then I went down and took, it's hard to explain how I got this 400 number, but I took an average between the highest of the low points and the lowest of the low points. Highest of the low points, but not way up underneath Glassford Hill. And that gave me 400 feet. That the Dells granite has eroded back about 400 feet in the last 13 million years. Now again, that works out to about 0.37, so about a third of an inch. So it's less. Well, the Dells granite is much harder than the Moenkopi. It's also very heavily fractured, and things that are fractured tend to erode, but this is a much harder rock. So I've said erosion rates clearly depend on the rock being eroded. They depend on many other things too. So this is where the simplification. I'm ignoring the vegetation. I'm ignoring the climate. I'm ignoring the amount of water. I'm ignoring all that. Okay. So this box that I made is faster erosion rates on the left and slower erosion rates on the right. So the faster one is the Moenkopi for what I just showed you for Red Butte. The middle one is the Dells granite, which I'm just showing you. And the one on the right I am proposing is the slower erosion of the Prescott granodiorite. That is our local, AKA blue granite, or peach, because they're the same. I know they're granodiorite, they're not really true granite, but never mind. And that's all covered in the book. That's the rock surrounding Thumb Butte. And if you go with a rough guess, maybe it's 1/10 of an inch in 1,000 years, remembering that the Moenkopi was roughly an inch in 1,000 years. And the Dells granite, roughly 1/3 of an inch. So this was just a guess. This is a guess. 1/10 of an inch? 1/10 of an inch in 1,000 years equals 125 feet in 15 million years. That's the most ludicrous statement you can make. I mean, yes, the math is correct. But there's all sorts of variables that I've ignored, okay? There's only 2 situations where granite systematically, gradually erodes. And that's when it's covered by running water, rushing water, or like when it scours out potholes on the bottom of a rushing stream, or when it's covered by flowing solid water, glaciers. You do actually get erosion of granite, just the gradual erosion, but otherwise other factors are usually more important. So me saying 125 feet in 15 million years is, like I said, a little ludicrous. But my takeaway at the bottom there is that I don't think that Thumb Butte and the areas surrounding Thumb Butte up there is that much different from what it was 13 million years ago, okay? I don't think it's radically different. I don't think Glassford Hill is radically different. That's 14 million years. 13 million is Glassford Hill. I don't think Glassford is radically different from how it looked when it was eroded. These are hard rocks we're dealing with, and hard rocks just don't erode that fast, especially we've had a pretty arid environment. These are really hard rocks, not like the Moenkopi. Okay. More on erosion. Well, I was talking about columnar jointing. Where did all those columns go? Long time passing. Oh, you can fill in the rest of the song there. Well, on the left-hand picture, I don't know if you can see the rock hammer. That's just a block that fell off. The red arrow in the middle picture shows you where those blocks were falling from. And this is my hypothetical imagination of the fact that Thumb Butte was bigger, and those columns have fallen off the top and fallen down. There's blocks all over there. So I don't think that most of it has been dissolved or ground away. I think that blocks have fallen off the sides, okay? That's my hypothetical picture there. Okay, now the last bit, theories about its formation. This one I'm not going to give a long explanation to. Some people have said maybe it's an example of inverse topography. That is when a lava flow fills a valley, and then the surrounding landscape erodes away, leaving the more resistant lava flow standing higher. There are examples of that all around Arizona, but that depends on the surrounding rocks being softer. And the surrounding rocks here are not softer. It's the AKA blue granite. So probably not. And if you look at it from the air, it's not linear. It doesn't look like it would be that way. I don't think Alan, who flew the flights in the 90s and took pictures for me, is here. But when you see that, now that we have Google Maps and all that, you can get these beautiful images from the air, but back 35 years ago, you couldn't see that. And he flew it, and I could see that it's not linear. So I don't think it's inverse topography. That it's the neck theory formation number 2, that it's the neck or plug of a now eroded volcano. There's no brecciation. It really doesn't look like it. And Shiprock has these beautiful radial dikes. And Thumb Butte does have a dike, but it's not radial. So I just don't think so. And again, the rock around Shiprock is very soft. And the rock surrounding Thumb Butte is not soft. That it's an example of a volcanic dome, and this was 25 years ago. I was thinking maybe it's a dome. Well, I put there perhaps, because I'm not a volcanologist, but probably not. Domes have really complex internal structure, which I've tried to show with those 5 little figures. And Thumb Butte doesn't have that. The flow directions are all the same, top to bottom, north to south, east to west, and the texture is the same. It doesn't look like a complicated, complex volcanic dome, okay? Theories about its formation. Number 4, that it's the remnant of a dike. There's a lovely light-colored dike in northern New Mexico. Again, you have to have softer rock surrounding them that can be weathered away, and that's what I showed you with Church Rock up there near Four Corners. Perhaps, but probably not. The columnar joining is vertical, not horizontal. The mineral orientation suggests one-directional flow. The rock texture is uniform, lacks brecciation, and the host rock is really hard. So I just can't get away from A, B, C, and D. So what this did was I just kept eliminating possibilities. And that's what there is the one dike. So where the red arrows are is there's that dike on Water Tower Hill, and some of you have been up there with me. It's not radial to Thumb Butte. But it is the same stuff. It is the same stuff as Thumb Butte. It's the only igneous material that's like Thumb Butte in the whole area, chemically. And so what I think is if this was the surface at the time, your dikes, your vents came up like this, and this one was Thumb Butte, and this one came up, and now it's been eroded down, so you see a little bit of an offshoot of the main vent that made Thumb Butte. Okay, elimination of the first 4. This is the drum roll. What is it? That the butte is the remnant of a vent-concealing lava flow. Its non-basaltic composition is a result of crustal assimilation or contamination as it ascended through the crust in non-coated conduits. And Jim Whitkey, who's up at NAU, where he may have just retired, wrote the same thing in 1981 about Hickey Formation lavas at the base, the oldest ones at the base of Woodshoots Mountain, which are the same composition as Thumb Butte, the oldest one. And I did not read that because I did all this work before the internet. I did not read that until after I'd written the article and come to these conclusions, which I'm glad for. I didn't have that influence. But he and I decided that the oldest stuff was influenced by coming up through non-coated conduits. Okay? Additional thoughts, and you can't see that, and I'm aware of it, so I'm just going to read this. This is essentially my last slide. So I'm just going to read it to you because I realize you can't read it. Lon Abbott, when he was at Prescott College, had a student who did a magnetometer survey on the butte. Note, the latite has a very high magnetic susceptibility relative to the surrounding granite diorite. He found the magnetic signal very high over the butte itself and a few narrow zones leading away from the butte, which he interpreted as dikes, and I could see the one. He wrote to me and he said, that doesn't say that the butte itself is a plug, but if it is a flow, it is the proximal portion that sits directly above the plug itself, not a distant flow remnant. And I agree that this is the flow right from, so where the red arrow, I said this was never published, so I haven't seen the data, but I think his information supports my explanation. So incorporation of his data suggests to me that perhaps the vent was a fissure oriented approximately north-south. The yellow area on my slide points to a small little vent and brecciated area on the lower front of Thumb Butte, and it's only about 15, 20 feet across. You can go up there and see it, it's right there. But I think the source of the lava that it makes the main portion of the butte itself came out where the red arrow is, on the high side, which is the south side. Based on the flow indicators within the rock, I assume the main vent was located higher up the slope, indicated with the red arrow. And that's all the flow indicators flow from that high side to the low. So that's kind of, there it is. If I'd known that it's Prescott's natural granite monument, I wouldn't have had to do all this work. Yeah. So I know that some of you have purchased a book. Thank you. I did not know that that the book was going to arrive. It got printed in South Korea. It took months and months and months. Debbie will tell you that she's been asking me for when the book would arrive for like 5 months? 5 years, okay, 5 years. I didn't know this was all going to happen at the same time. It's kind of been a little overwhelming. And then they asked me to talk, and I said, well, what would you want me to talk about? I don't know what to talk about. Do you want to hear about Thumb Butte? And they said yes. So I will tell you that there is a section. I think there are 27 sections in the book. Some are very short. Thumb Butte is the longest one. So what I've just covered here is the section of Thumb Butte in the book. The fellow who asked me about the pink rock, that section is pretty short. Pink rock around town. Or the Gail Gardner landslide, that's pretty short. You didn't know about the Gail Gardner landslide. There you are. Anyway, I think...
Big thank you to Beth. And then we have time for a couple questions, and I'm going to attempt to pass the microphone around so our live stream audience and this huge audience can also hear the questions. Do we have any questions?
I know there was someone in back. Ron Harvey.
Okay, we got a microphone coming to you.
He has to be one of my earliest students.
Yes.
Was it 2000?
Hello. There we go. It was further back than that. It was 91. Yeah. So.
You age well.
Well, thank you. Likewise. So I'm curious about Little Thumb Butte out near Chino. And is it similarly formed to Thumb Butte?
Well, it's part of the Sullivan Buttes,
Mm-hmm.
so it's probably in the 25, 26, 27 million. The Sullivan Buttes is a whole wide range there are known domes there, there are known little plugs there, and there are lots of known flows. I think that Little Thumb Butte is just a flow like this.
Okay.
Yeah. There are lots of NAU geology master's theses written about the Sullivan Buttes.
Oh, cool. Okay, thank you.
You're welcome. 91.
Other question? I'm going this way.
Thanks. Just two, yes, no? Two quick ones. Any idea how extensive the lava flow might have been, the Thumb Butte one? And second, related, any flow direction studies on the water tower?
The water tower one is a dike.
Okay.
So it was dike, it was just confined. How do I think it was more extensive? If you can stand out there, if we look through the windows and look out, I think that it was twice as wide as it is now. But no, I don't think it went miles. I think it went 50 yards or 100 feet on each side and 150 feet in front of it. I don't think it was far greater than that particular flow. Now, around town, I'm sure many of you hike. If it rains, if it ever rains again, when it rains and a trail gets sticky and muddy, that's because that was underlain by basalt. That trail, even if you can't see that it's an old lava flow now, it was, because that's what makes it sticky. You know all the other ones, you go out with a pea vine and you go out and it's just sandy. It's just grainy and sandy and it doesn't stick to your boots. That's granite. You can tell the minute it's been wet whether you were walking on old weathered basalt, sticky, messy stuff. Oh, try to hike out there Williamson Valley after it's rained. Oh God, abandon hope. Or the other stuff is the grainy stuff, and that's because it's on granite, okay? Did that help? So there are lots of flows around town, but Thumb Butte doesn't go very far. Okay.
At Sullivan Dam and Lake.
I know who you are. It's been bugging
headwater-
me for an hour now. I know who you are.
At Sullivan Dam and Lake is kind of the mile zero on the Verde River, and there's a basalt cap that overlays the Martin Formation.
Yes, yes.
How old is that basalt cap? Where did it come from? I've never gotten a straight answer from a geologist, so I thought I'd spring it on you.
I can't tell you right off the top of my head, but I can look it up for you. And I know who you are. You were at Yavapai College before, a long time before even Rod. Yeah, yeah.
Is there a question over here?
I will get, because of CWAG, I can get a hold of you. Yeah, I don't know the answer off the top of my head.
Is there any information on cooling rates based on depth from surface with, volcanic magma plumes and whatever shape they're in?
There's lots of information that relates to the thickness of a surface flow and how fast it cools to the interior until the interior goes through the oh God, I just lost the name of that word. Till it gets below 570 degrees centigrade. But as far as magma bodies underground, I'm sure people have done work on that, but it's not me. One of the things about magma bodies is like what's underneath Yellowstone is they're not static. There's slow churning and slow recharge from below. So I'm not sure I'm even attempting to answer your question. But lava flows at the surface, thick lava flows, yeah, they've got like Hawaii. They can tell you how fast it goes through the Curie point temperature. Thank you, the Curie point temperature. They can tell you how fast a 30-foot thick basaltic lava flow, the temperature of the center of it goes through the Curie point. It's like 2 weeks. It's quick.
Okay, last question.
I am one of these guys that's a dreaded soil engineer that has to deal with unconsolidated rock. My question is, in all of the good literature reviews that you've done, and it seems to be pretty exhaustive, have you come across any studies of the derivative from, say, the basalts in terms of the clays?
Oh, yes. Well, I mean, all of our clays and our basalts here all of our clays in our soils here come from those basalts.
That's what I thought.
Yes.
But I'm asking, is there any deeper study about the characteristics of that would help a guy like me?
I bet there are, and I don't know them.
Okay. Well, can we talk?
Sure.
Okay.
Sure. I bet there are. And I want to go back to the one question before, just real quick. I don't know if any of you ever heard of the Steens Mountain Conundrum. One of the things that's cool about cooling lava flows, if they're basalts, they contain enough little magnetite grains that they will orient, let's say the back of the room there, the fellow in the orange shirt, you're the north magnetic pole. And if we have a lava flow and all these magnetite grains and it's really hot and runny, as the lava flow cools, they will all orient in the direction of Earth's magnetic field. And that's how they get these old field directions or the old pole directions. Well, there's a place in the Steens Mountain in Oregon, and everybody wants to know, how fast do these pole reversals happen? Do they take 10 years, 100 years, 1,000 years, a million years, right? Well, there's a place in the Steens Mountain where there's a 30-foot, it might be 50, but 30, 50-foot thick lava flow that they've age dated. So they know the date, and it's roughly 15 million years. This is when it was erupted. And so based on studying Hawaiian lava flows, they know that it takes roughly 2 weeks to cool to that Curie point, which is the point temperature at which that magnetic direction is set forever. So in the lava flow that thick, it should take about 2 weeks for the center of it to take the direction that's permanent. Then doesn't matter what happens, it's hard rock now and it's going to preserve that orientation. Well, in the Steens Mountain flows, the outside points this way, and you get into the center, and all the magnetite grains indicate the opposite direction. That's 2 weeks. And it's called the Steens Mountain Conundrum because when they first published on it in '93, everybody said, "Ooh, boy, did they screw up. We're going to send people out and we're going to prove them wrong." No one has proved it wrong. And they've sent, lots of universities have sent. And in fact, they found another one near Battle Mountain, Nevada, which is not far from the Steens Mountain, that shows the same thing. So there are still plenty of things to learn, plenty to know. It's a fascinating science. I'm glad you're interested in it. Thank you so much for coming. Thank you for your interest.
Thank you, Beth. We have an NHI hat for you. Thank you all for coming. Please visit the Peregrine Bookstores booth and also the NHI one once you leave. Thank you.